the screen. Just give me a second. Okay, is the screen now visible?
Yes, sir.
Yes. Okay. So I think we finished. We stopped with IoT communication topologies. Next, we have to look at what is referred to as the constrained devices, and we will look at what are constrained networks. So these are the terminologies which are very commonly used when we design an IoT based system. And please remember that when we talk about an IoT network, we are not talking about something that you do using 2 or 3 microcontroller boards. We are talking about a huge network which may involve hundreds or maybe possibly thousands of IoT nodes. So in that case, every single choice that you make will have a critical impact on the cost and the uh, communication as well as the resource consumption in the overall network. So please be very careful about this. Do not think that just putting 2 or 3 Arduinos together will form an IoT network, which is what everybody does. They don't do that. In industry, it's usually nodes of hundreds or possibly thousands of nodes together. Okay, so we have to be very careful when we make the definitions. So far, what we have done is we have had a look at all these things. Now we are having a look at constrained devices. Okay, so the other things we have already covered. We are looking at constrained devices now. So how do you define the constrained devices or constrained nodes? Typically, uh, the definitions on these aspects is done by the IETF, which is the Internet Engineering Task Force. You can go to the internet and just type IETF and you will go to their homepage. What they do is they kind of define the terminology, they define the standards. If there is any issue with, or if there is any clash with the ways in which systems are implemented, they try to sort that out and so on. Okay, so it's one of the major standardization bodies which also works with IoT systems. Typically, they are defined for internet systems, but IoT also is one of their major kind of focus areas, and they try to make sure that there is no discrepancy in the way that it is defined and so on. Okay, so what they do is they have come up with a common terminology which everybody kind of tends to use. So if you are making an IoT network and somebody else, maybe say uh, for example, say you are working for some company, say Robert Bosch, you make an IoT network, and then you move on to some other company like say NVIDIA or something else. Somebody else who is new comes into the project that you have been working on, and he wants to learn what you have done. So there should not be any confusion regarding the terminology that you used and that that person has been used to using. So a standard definition set has to be available. So that is one such requirement. The clients should be able to understand what you are trying to say. Your colleagues should be able to understand. The other third-party vendors should be able to understand. That is the requirement why we have standard terminology for most of the devices that we have. And the definition was actually put in terms of RFC 7228. RFC is request for comments. Okay, so IETF frequently brings out these things as RFCs. So basically what they have is they have a document and they will look at the comments that are coming in from the people who are stakeholders in this, and based on that they will either refine it or they will abandon it or they will keep it as it is and so on. So this also is available in the internet. You can just check RFC 7228. You will be able to see the document there. You can download its PDF version or you can look at the text file or whatever you want. It's freely available. Okay. So according to their RFC 7228, what they have is they have defined what is a constrained device. Okay. Typically, the need for defining a constrained device comes into picture because they want to keep it separate from the idea of non-constrained devices such as say laptops and so on. Okay, because that also is a mobile system. Your laptop is also a mobile device. It also has a battery. Your mobile phone or your smartphone is also a mobile device. It also has a battery. So how do you kind of distinguish these kind of devices from what you need in a constrained system. That means obviously you will not be using laptops as nodes at all times. It's not feasible. Similarly, you will not be using your mobile phones as nodes in all the places. That is also not feasible because cost wise, computation wise, a lot of irrelevance comes into picture. So you don't want to do this. You can technically do that, but you won't want to do that because you are talking about a 1,000 node network or a 2,000 node network. So putting 2,000 mobile phones for something like say measurement of temperature over one say district. So you want to measure the temperature all over Coimbatore. You will be using something which is cheaper rather than 2,000 smartphones spread out over the city, right? So that is the idea. You want to use only as much computational power as required because cost is almost directly proportional to the computational power that you have. More powerful your system, more costlier it gets, and usually more battery it consumes. So it's a trade-off. So you try to minimize the cost, you try to minimize the computational requirement, and so on and so forth. Right. So what we do is we need to have a proper definition on what is a constrained device. So the constrained devices uh, are of multiple types. Okay. So the constrained devices are typically categorized based on these aspects: how much flash it has, how much RAM does it have, what is the kind of CPU that you have, how do you supply the energy, and how do you update or configure the device. These are the 5 major aspects based on which you define the type of constraint node. I think the first part you may have already gone through. The first two you must have already understood the problems of flash and RAM. Have you done any course on embedded systems, or have you?
Yes, sir.
Yes. So if you have done any microcontroller programming, you will know that there is a maximum size of code which you can burn into the microcontroller. If you have used Arduino, you're aware of that.
Yes, sir.
Yes. So the larger the flash that you have, the larger is the program that you can put into the microcontroller board. That is why you have multiple different types of Arduinos, right? So you have Arduino Nano, you have Arduino Uno, you have Arduino Mega, you have Arduino Duo. So there are several versions available, and all of them kind of slightly vary based on the processing ARM uh, architecture that they have, and also on the flash size they have, right? So if you have a very small flash, you can program very small programs on it. If you have a larger program, it will not burn onto the board itself. So you will have issues with that. So obviously, and typically what happens is if you have a smaller flash size, it will be a lot cheaper. Smaller flash means cheaper microcontroller. So that is why you have Arduino Nano is typically cheaper than Arduino Uno. And Arduino Uno is always cheaper than Arduino Mega. Right? So it goes on like this. So the cheaper boards obviously support lesser flash. The reason for that mainly is because like putting bigger flash costs more money to fabricate. That is the only reason, right? And then you have the idea of RAM, right? You also know what is the typically the RAM size that you have. It will be like 64 KB, 32 KB for smaller boards, and for larger ones you have a larger uh, capacity. What is the problem with a smaller RAM? Any ideas? With a typical IoT node, if you have a smaller RAM, what will happen?
We can't have a track of lot of data, sir.
Yes, the thing is that if you have a smaller RAM, uh, please remember that smaller IoT nodes will not have any operating system on them, right? So you cannot say that the operating system will become slow. Just like your Windows becomes slower when you have a lower RAM, because most of the IoT nodes won't have an operating system. The system will run equally well if you have a larger RAM or a smaller RAM. Unfortunately, the thing is that if you have a smaller RAM, you cannot store a large amount of data in the buffer. It's basically like a buffer that you have. right? For example, if you want to store 100 values before you start processing, some of the RAM, some of the microcontroller boards may not allow you to do that. Some other boards which will have a larger RAM will allow you to store 200, 300 values in your RAM before you can do the processing. One example I'll give you. We were actually trying to develop a filter to kind of filter out the vibrations in the data that we were collecting. And the filter that we found out was something like a moving average filter. It's a low pass filter, obviously, right? So the simplest low pass filter will be a moving average filter. And the number of values, or the moving average window that we selected, was 50. Which basically meant that I would need at any point of time 50 values to be available in my RAM. Okay, then I will just, once 50 values are available in my RAM, I will just take the average of that and pick that value and place it there as a single value, which will filter out all the extra noise which is coming in. So the problem was that I needed 50 values to sit in the RAM at all points of time. And this is not possible if you have a nano or something like that. You cannot put that many number of floating point numbers in the RAM if you have a very low quality microcontroller. Maybe I don't think it is even possible with a node MCU. So smaller devices will have a problem because you cannot put a lot of things in the storage. You can write them in the external memory, or you can write them in the flash space that may be available after program, but you will not be able to use them dynamically. That is a problem that you will face. Okay, so that's a problem typically that you have when you have a very small amount of RAM. So you will have to rework your code in such a way that you can do it with a smaller size of RAM and so on and so forth. Okay, so that is why the RAM is such an important aspect. Okay, so you may have come across this constraint when you were doing microcontroller programming, but it is a very, very common problem that many of us face, especially when you're dealing with things like signal processing or filtering operations or stuff like that, because you require some amount of data to remain in the memory when the processing is going on. So unfortunately, it kind of creates a lot of issues like this. Or maybe when you are kind of reading the data and pushing it into the cloud. So the writing to the cloud or moving the data to the cloud can be a slow process. So the data which is coming in just continuously comes in and kind of creates a backlog. So beyond a particular value, the stack kind of overflows and you are not able to log in more values. That is another problem that you will face when you have a smaller RAM. So there are several problems that you will face with a smaller RAM also. Right? Uh, does it make sense? I don't know. I don't know how many of you have actually experienced this, but does it make sense to you?
Yes, sir.
Yes. Okay. So that's what happens when you have a smaller RAM. And the third problem that you will have is obviously the issue of processing power. Most of the boards that you will see now are also kind of classified based on what kind of processing power you need. You have separate kind of boards which can do DSP processing, like a not Tata, I mean like the Texas Instruments. You have these TMS boards which can do signal processing very nicely. You have ARM boards which can work on different. There are several different ARM architectures which are now available. You have Cortex boards, you have Citra, you have so many different architectures of ARM are now available, which can have a lot of processing power. And on the other hand, you have the small architectures, like typically just simple RISC architectures, which can be used for smaller applications like your Arduino, Uno, and so on. Right, so very, very simple architectures are also available which can do smaller kind of processing. So more complicated your application, more powerful your board will have to be, which means that more will be the computational requirements, and which means that there will be more amount of energy loss which will be happening, and obviously the cost also will increase. Please remember that ARM is a company which licenses its architectures to manufacturers. Okay, so when you talk about ARM based microcontroller, ARM is an architecture which is a proprietary architecture made by a company in UK. It is called as ARM. Okay, so ARM kind of licenses out its architecture to all the people who actually build these devices. Okay, so Atmel kind of makes these kind of boards. So ARM will license its technology to Atmel. Atmel will make the microcontrollers. So the manufacturer will be Atmel, but the technology or the architecture of the microcontroller will be provided by ARM. So it's like a IP provider, intellectual property provider is ARM, and that is why every microcontroller that Atmel will make using ARM architecture, a small amount of licensing fee will go to ARM. And that is why for more complicated architectures, ARM will charge more money. So Atmel will make it and give more charging, more amount to ARM. So that is why you see that ARM boards kind of have different costs based on how much licensing fee needs to be paid to ARM. Okay, so as far as I know, ARM is one of the made the only kind of a company which has become hugely successful just by selling their IP. They don't physically manufacture devices; they just sell their intellectual property. They license it out and they make money out of that. So ARM does not have any fab. ARM does not make any microcontrollers per se. It just licenses out its technology, and companies right from Qualcomm to Broadcom to Atmel, everybody kind of uses their architecture to make these boards. Right. So processing power is an important aspect in that case, because cost will also depend directly upon how much processing power you have, and so will be the battery life. Okay. And the fourth criteria that you have to look at is what is the energy or the power supply. I had to put a slash here, I forgot. How much is the energy consumption, or what is the power supply source you have? That is also very important. Why it is important? It is important because if you have a ready-made source of power supply, you can use more. You do not have to bother much about energy consumption. You don't have to optimize your code to uh, say use as little amount of energy as possible. You can just play around with the code and make sure that even if it is inefficient, it does not matter, because you are supplying it through the mains power supply, which is a reliable power grid supply is available. So okay. But on the other hand, if you are putting it on some remote location where battery has to be used, you have to be very careful with every single milliwatt of power that you are using. So there is, you have to code your program in such a manner that it has to be done properly, and every single transistor switching that happens will result in power consumption. So you have to pick and choose your commands, pick and choose your mnemonics, pick and choose your uh, code in such a way that the consumption is as little as possible. All these things will come into picture once you actually get into the field and start working. What appears very easy for you may not be that easy once you get into the field actually. Every milliwatt of energy power that is being used up will have an impact on the battery life. So be careful with that part also. And the last thing that you have to be careful about is what is the ability, how much ability you have to configure such devices. Can you do remote configuration of devices? Can you do you have to go to the field and do this? Sometimes what happens is that some devices, if they are made very cheap, they are completely frozen when they're coming out of the fab itself. That means you have no option to reconfigure them. They are factory configured and you can only use them as it is. They tend to be very cheap, but the thing is that customizability is very low. But on the other hand, you have boards which IoT nodes which you can auto configure through software push. Now I think you can see that in your mobile phone also. You can push your updates and the phone will automatically update to the newest version of Android or iOS, whatever you may have. So that can be done with your normal IoT nodes also. You can push new functionality into it. You can update it. You can kind of, if there are any software patches that need to be put in, you can put those in. But again, the problem with those kind of systems is that auto reconfiguration is supported only for more complicated boards. Arduino, I tried, but I could not update it online. Like when it is functioning, it doesn't update. Has anyone tried that? Runtime updates? Hello? Am I audible? Did I lose you people? Yes.
Yes, sir.
Yes, right.
Yeah, okay. Like, have you tried like runtime reconfiguration kind of a technique with any of the Arduino or any other boards that you have done before?
No, sir.
Sir, you mean like updating the firmware while it's running, like
Up,
flashing it?
uh, yeah, but that flashing, the idea was that I wanted the system to run as it is. Say, for example, I am measuring the temperature. So that program will be running here, but I should be able to add new functionality dynamically. But that I don't think is supported with Arduino, right? For example, I want to kind of add the functionality to measure both temperature and pressure at the same time. But the system should not go off air, maybe for a couple of seconds, but not more than that. That I don't think is possible with Arduino Uno or something like that. Has anyone tried that out? Basically, that will require flashing. Arduino, I don't think will have. Arduino Uno does not have that option, I think. Has anyone tried that with any of the versions of Arduino or any other board? Runtime reconfiguration kind of thing?
No, sir.
Sir, but flashing itself takes like only a few seconds, right?
Which one? I could not
L-
hear it.
Like flashing, like the new, what do you say? Program will only take a few seconds in the first place.
No, no. What I wanted was that this should kind of keep on running, adding new functionality onto this.
Right, right, sir.
Because otherwise you're reprogramming the whole system all over again, no?
Right, right, sir.
And then you lose all of the stuff. I mean, like, I don't want to make any changes to the hardware, but I should be able to add new functionality. I should be able to keep all the data which was already there. So on and so forth, without using an additional hardware. Like, I don't want to write it to separate RAM or flash and then pick it up back from there and stuff like that. The idea was to use runtime reconfiguration. Uh, I tried with some FPGAs. Some FPGAs actually allow you to do that. Have you done anything with digital design? FPGAs have you worked with?
I don't think so, sir.
In digital design course, you have done something with that? Did you have a course on digital systems design?
Yes, sir.
Did you work with VHDL or Verilog or anything of that sort?
No, sir. It was just the basics.
It was just
It was just about basics, sir. Like,
okay. Okay, so you have no exposure to VHDL or Verilog or anything of that sort?
no, sir.
Okay. So actually, there is something called like, you can actually have digital. Um, what do you say? We call it as hardware definition languages, HDLs. So you have like VHDL, and there are two languages which are commonly used for hardware description languages. So you have these kind of two commonly used languages which are used for programming what is called field programmable gate arrays, or FPGAs. Um, so you can kind of whatever digital systems you have learned, like counter, um, say whatever you have learned, timers, counters, all those things that you have learned in your digital design, you can realize in hardware also. And that board is called typically an FPGA, field programmable gate array. So you have Xilinx as one of the major players in this market, and you can actually realize an entire microcontroller inside an FPGA. An FPGA can be configured as anything you want. The whole FPGA board can become one giant counter. The whole FPGA can become one giant timer. So whatever digital system you want to program into it, or you can make a whole FPGA into one single AND gate, or you can convert that FPGA into 1000 AND gates, each being given as one input. So any possibility is there. FPGAs are very exciting to work with. So you can actually do things like that. And uh, when I was working with FPGAs, I tried to do dynamic reconfiguration. I wanted to kind of convert that whole architecture into something else when the processor was running itself. So there is partial reconfigurability which was allowed at that time. Now I'm not very sure, but full reconfigurability is something that scientists are still working on. Runtime reconfigurability is something which is a very exciting topic to look at. So if you're going for maybe your master's or something, you could look at that as one of the topics to deal with. Runtime reconfigurability, especially for such low, what you may call it as low processing power applications and stuff like that. Okay, so the system will work continuously, but you will be able to add functionality or remove functionality during runtime. So it's not like you flash the whole thing again and then something else comes up. During the running itself, this will happen. Runtime reconfigurability. That is something that you could actually look at as an exciting thing to work with. Okay, so anyway, let's get to the next slide. So can you see the next slide now? 3 different classes.
Yes, sir.
Yeah. So these are the 3 different classes of constraint nodes that RFC 7228 kind of talks about. Okay, so you have class 0, class 1, and class 2. So you have RAM sizes varying between, this actually means much less than 10 KB. Okay, so very small processing. So class 1 has up to 10K, class 2 has got up to 50K, and flash will be of different sizes, 100, 250, and so on. So you have very highly constrained nodes as class 0. The nodes which are kind of okay, this is something that we can manage with class 1, and class 2 is kind of reasonably good. Will be very comfortable programming with something like this, right? Unfortunately, the problem is cost wise, there will be a huge difference in the prices. So the more the RAM and flash you have, the more costlier the device will be. So traditionally, when you talk about a class 0 constraint node, you're talking about something which you can expect to have a RAM of much less than 10 KB and flash much less than 100 KB. So if your client comes and says that I have got only class 1 constrained nodes, it basically means that this is the limit that you have. Okay, and similarly, if your client comes and tells you that I have got 1000 nodes of class 2 constrained nodes, this is what you have. So you have to design all your coding and all your data requirements around this requirement, that this is the maximum you are going to get. Okay, so that's what you have: class 0, class 1, and class 2. Is it okay? Can we go to the next slide?
Yes, sir.
So this is the description. Right. So obviously there are some very obvious truths that you can see here. Class 0, you do not have any possibility to implement any kind of an IP stack with this. There will be zero possibility of putting up some kind of security, etc. And remember one thing, now you have the bigger boards that you get, they usually come with an encryption chip also built into them. Have you seen any of those boards? Hello? Hello? Am I audible?
Yes, sir.
Yeah, so more recent versions of Arduino, some higher versions of Arduino, you will see they come with a dedicated chip for encryption also. So it's outside the board, like outside the main microcontroller, but it's a dedicated board. Just like you have a separate board for separate microcontroller for Bluetooth connectivity and separate microcontroller board for Wi-Fi, you have a separate small chip which will be integrated, which is for only for security. The reason is because if you have a very small microcontroller and you are transmitting the data over something, it is very easy to eavesdrop into that and hack into your or read your data that you are transmitting. But if you want to protect your data that you are transmitting, you need to have some kind of security built onto it. So class 0 devices, because they have very little memory, it is almost impossible to implement any kind of security on the microcontroller chip itself. So you may have some additional boards, additional chips which are kind of doing this. Okay, so that is the thing. And if you have class 1, again you have, because you cannot implement IP stack on it, because still again, if you want to implement different protocols on different layers, you require more and more memory. That also is not happening. So class 1 also is kind of okay, but class 2 devices can do proper implementation of at least some part of the IP stack. So you can integrate typically with IP networks. You can have a smart energy meter and so on and so forth, which can directly connect to the internet and transfer the data and so on. So configuring class 2 devices is very, very easy. You can do that very quickly. You can set them up fast and you can make them work. Unfortunately, cost wise, they will be heavy. Okay, just give me 1 second. I'll just show you what I mean by the security and the IP stack. Just 1 second. I think we're almost out of time, so just give me 2 seconds. I'll try to find out.
Sir, are there classes higher than class 2?
Yes, there are other. Typically, anything above class 2 is kind of considered in the same category. But according to RFC 7228, they only kind of consider these 3 classes. Okay, just 1 second. Yeah, this is what I wanted to show you. 1 second. Let me share the screen. Can you see the screen now?
Yes, sir.
Arduino Uno Wi-Fi. Yeah, so here you will see they have this Bluetooth, and then you have here. Can you see the secure element? This is added as a separate module to add more security to the system. So if you click on this, you will see that it will open. Can you see the datasheet now? Microchip.
Yes, sir.
Yeah. So this is actually the cryptographic coprocessor that we are talking about. So there is a separate kind of a board which will help you with the authentication and the security. See, it will do all these things. So you don't have to manually do this. It will automatically be able to provide you with security. So I don't think your traditional Arduino Uno had this, but Arduino Uno Wi-Fi Rev 2 kind of has all this. It also has a Wi-Fi module built into it. So I use this for most of my applications because I did not want to add a separate ESP8266 or board to get Wi-Fi. This is very easy to work with. So you have everything here. You have the accelerometer, you have the Bluetooth module, you have the, as I said, the security is built in. So many things. It's kind of quite good. It's available in India also. You can have a look at it. So this is what I wanted to show you. I mean, like security will typically be in the form of a separate chip for almost all of these cases. And the more complicated your microcontroller, they will kind of become inboard. So they will be implemented inside. That's how it goes. Okay. So any questions so far on the topics that we have seen? 3 classes of devices.
No, sir.
So if there is nothing else that you need to do, I understand that there is a lot of theory going on here, but because this syllabus is like this, we will be doing this, and hopefully as we kind of reach the 4th module, I will try to give you some additional material which will kind of help you understand this better. We will try to configure some of these kind of devices and see what can be done. At least online itself, we'll try to do this. Okay, so let's wait for one more module. Once you are okay with this, we'll try to do something. Okay, so Fine. So if there are no questions, I think we can break for now. Any queries?
No, sir.
Okay, then thank you all for attending. We'll continue in the next class. Bye.
Thank you, sir.
Thank you, sir.